Have you put your data to work? Brookhuis Applied Data Intelligence makes a series of e-learning videos on clean rooms. This one is number 5. It will be on particle deposition rate. I will explain how we express particle deposition rate and what's the relation with air cleanliness and surface cleanliness, and how you can use it to estimate the contamination risk of your product. So first I will explain the expression of particle deposition rate and particle deposition rate level in relation to the two different standards which are around. I will discuss mechanisms of particle deposition, sources of particle deposition, and the relation between particle deposition rate and air cleanliness, particle deposition rate and surface cleanliness, and the relation between particle deposition rate and product contamination. Particle deposition rate is the number of particles depositing per square meter per hour. The particle size is either expressed in 1 micrometer or in 10 micrometer, but the relation between the number of particles and the different particle sizes is that the number times the size is constant. So the number of particles which are deposited per square meter per hour are proportional to the particle size. The particle deposition rate level is in fact the product between the particle deposition rate of a specific particle size and the particle size. When you have a clean room at rest, the particle deposition rate is 0. The particle deposition rate depends on the air cleanliness. We have already discussed how you can measure air cleanliness with a particle counter, but a particle counter doesn't give you the information on the particles which cannot be removed by airflow. The particle deposition rate is in fact the concentration of these microparticles times the deposition velocity of the microparticles. So simply PDR is C times U, which I have used for a particle deposition velocity, but to be precise you have to write it down for certain sizes, and that's why I use this subscripts D when I really want to point out a specific particle size. The deposition velocity depends on the size of the particle, on the type, on the mass. So a metal particle is heavier, has a higher specific density than a sand particle or a skin particle, but also the shape. If it's a flake which goes down slowly, you have a different velocity. So, and the next factor is of course the local air movement, because in the clean room air moves around, so this will also affect the movement of a particle. How I normally look at this is I have a pocket of air, and in this pocket particles are falling down, and this pocket of air is moving through the clean room and passing also along a product surface, and then when a particle is just at the bottom of this pocket, it will fall onto the surface. If not, it will just be carried away. I will describe two standards on particle deposition rate. A standard which was published in 2014 is made by the Dutch Contamination Control Society, VCCN, and it uses in fact ISO 14644 part 9 on surface cleanliness, and it looks really at the change of this surface cleanliness over time. So that means that we look at the number of particles larger or equal 1 micrometer per square meter per hour, and these numbers can be very high. So just like surface cleanliness, we take the logarithmic value and we create a particle deposition class. So a particle deposition class of 4 means that we have 10,000 particles largely equal 1 micrometer per square meter per hour. Again, in the table you have different columns for the different particle sizes, 1, 5, 10, 20, 50, 100 and so on, up to 500. Just in the same way as is done with the ISO standard on surface cleanliness. And there are 6 different particle deposition classes specified. The particle deposition rate is in fact then 10 to the power of this particle deposition class divided by the particle size of interest. And the reference particle size is 1 micrometer. So you can also say the particle deposition rate level is in fact the particle deposition rate times the particle size. And when you take the logarithmic value, then you have your particle deposition class. At the moment, the ISO Technical Committee 209 is working on a new standard for particle deposition. This will be ISO 14644 Part 17, and in 2019 the draft international standard will be published. And here the particle deposition rate is defined as the particle deposition rate level divided by particles largely equal 10 micrometers, or when I put it in formula, this particle size d divided by 10. And when you multiply these, particle deposition rate times d divided by 10, then you get the particle deposition rate level as defined in the new standard on particle deposition. And then we get different particle deposition rate levels from 1 to 1 million. And when you have, for instance, particle deposition rate level 10,000, that means 10,000 particles larger than 10 micrometers per square meter per hour. And here again, we have different columns for the different particle sizes. So I was explaining already a little bit that when you have a pocket of air with larger particles, they can be they can be deposited onto surfaces by sedimentation or just by interception. It depends on the boundary layer, because sometimes you have a boundary layer and then it's more difficult for a particle to come from the pocket of air onto the surface. Electrical forces can help a little bit with that, but the most important one is the extra momentum you can give to a particle by turbulent airflow. And then a particle can just leave your airflow and bump onto a surface and get deposited. We have also done some tests with objects and look at airflow around objects, and then you see that in the area have a high turbulence, you have also relative more particle deposition. Well, when we understand how particles can be deposited onto a surface, then the next question is, where do these particles come from? Because in a clean room, at rest, there's no particle deposition. So where do they come from? Well, when we start using a clean room, people enter the clean room, people put on clean room garments, they act as a filter between the person that is generating millions of particles and the environment. But still, a few particles can penetrate these garments. But also during changing, you can get particles on your garment on the outside, and those you bring inside the clean room. So the number of people, the type of garments, the procedure of changing from normal street clothes into clean room clothes is important, and also how well you execute it. So how good is your discipline, and the type of movements you make in your clean room. They determine how many particles from a person will come into the air and can deposit on surfaces again. Also, when people are working in the clean room, the working methods, how fast they move, how do they move in relation to critical services, they are all important in the local air cleanliness with respect to macroparticles. unclean surfaces, when particles are there, are no problem until you get some turbulent airflow caused by activities. Then particles can come into the air and can drop down again. Equipment, moving parts in equipment can cause particle deposition, but also if the inside of equipment is not cleaned well, it's open, then many particles can come into the air and deposit onto surfaces. So when we look at people and we look at the garments, then you can see that these garments, they act like a screen, like a simple filter. But these filters, they have holes, and through these holes particles can still penetrate, because a particle is not a sphere but often a fiber, and a small fiber can easily go through a hole and come into the air. So I've found some data on the emission of particles by people when they wear normal street clothes, and in general the number of particles decreases with the particle size, and when you put on a clean room smock, a clean room coat, then this number of particles will be reduced, because you protect already a part of the body of a person. It will be better when you cover a person completely, and you can even improve it further when you also change the undergarments of a person. Then you really keep all the particles which a person is generating inside the garments. So that means that the better the garments, the less particles will be transferred into the surrounding air. I've also put some data from a publication of 2006, where the number of particles larger than half a micrometer, larger than 5 micrometers, and the microorganisms, which are more or less in the order of 20-25 micrometers or more, I've been put them into this model, and they fit quite well. So these data can be used to calculate the impact of a person on the particle deposition rate in the room. So we have had now sections on air cleanliness, surface cleanliness. I've explained particle deposition rate. So in a clean room, we have standards for how clean is the air, how clean is the surface, but we also know that we have a transfer of particles from the air onto the surface. This dynamic component is the particle deposition rate. So when this is a dynamic component in your clean room, then also the dynamics of your airflow is important. So the ventilation. The more ventilation you have in a clean room, the better particles can be moved out of the clean room. We do not know how well this works, so recently we made a study, and we collected some data in a test clean room, which is 2.7 meters high, and we had about 54 cubic meters per hour, which came into an air change rate of about 20. And we have been measuring and calculating how well is the removal efficiency of the ventilation of larger particles, which I will show you in the next graph. So you can see that when you look at particles larger than 5 micrometers, that still 95% is being removed by airflow. But when you move to 10 micrometers, 20, 50, you see that the removal efficiency is dropping down very fast. Down to 50 micrometers, then only 10% is still removed. And the particles which are not removed by airflow, they are being deposited on all the surfaces in the clean room. So it's interesting, when you put these two graphs together, you see some kind of midpoint where 50% of the particles is deposited and 50% of the particles is being removed by airflow. In this case, that's you find this midpoint at 15 micrometers. If you increase the ventilation, so the number of air changes, then this midpoint will move to larger particles, and if you decrease your ventilation, it will go to smaller particle sizes. I'll show that in the next graph. So in this graph we have 4 different air change rates in the clean room, and you can see that the 50% point is moving from 7.5 micrometers up to 25 micrometers at 60 air changes, which is already a lot of air. So you can improve this removal a little bit, and by removing the larger particles a little bit better in the clean room, you can reduce your particle deposition rate. But it's much more sensible to remove the larger particles from your clean room by better cleaning, and to limit the introduction of particles by having a better discipline, because then you don't need so much air and you can save a lot of energy. So it's very interesting to know this relation between the concentration of particles larger than 5 micrometers and the particle deposition rate, because then you at least know what the minimum specification of your clean room should be. But I hope also to have explained that how you use your clean room will determine how many large particles you will have, and that will in fact determine the particle deposition rate. So particle deposition rate tells you what the situation is, but you can also try to achieve a certain particle deposition rate. So that's what I wanted to tell you about particle deposition rate and particle deposition rate level in this section. I thank you very much for your attention, and soon we'll make some more videos on contamination control and risk assessment on product contamination.